Hello, in the previous video we studied linear transformations. We talked about each linear transformation is corresponding to some matrix. And today we will consider more examples on the relations between matrices and linear transformations. Okay, suppose you have a linear transformation from R3 to R3 and T1 x2 x3 equal to 2x1 plus x2 minus x3 negative x1 plus 3x2 plus 3x3 and then 3x3 minus x1. Let's find the matrix of this linear transformation. Okay, so we know that Tx equal to ATX. Or, it depends on how we write this relation. Sometimes you may see Tx transpose equal to ATX or Tx equal to ATX transpose. All right, so from this relation, we can see actually the matrix AT is nothing but 2, 1, negative 1, negative 1, 3, 3, negative 1, 0, and 3. How can we see that? So look at this. The first coordinate of Tx1, x2, x3. That is corresponding to the first row in AT. I just pick coefficients from here. 2, here I have 1, and here I have negative 1, and write them in the row form. Makes sense? For the second one, I pick the second coordinate in T and pick all entries, all coefficients of x1, x2, x3 in here, and I write them in the second row. For the last, I pick the last entries of T, and then I pick coefficients right here, this negative 1 for x1. I have 0x2, so I write 0 right here, and I have 3x3, I have 3 right here. That's how we can write the matrix of a linear transformation if you know the form of that linear transformation. Okay, let's verify that. That is AT, okay? Now let's apply AT to x1, x2, and x3. So let's say x, okay? I have, this is 3 by 1, 3 by 3. We have 3 by 1 in here. So at the end, you should have 3 by 1 matrix. When you multiply them, you have 2x1 plus x2 minus x3. And then negative x1 plus 3x2 plus 3x3 and negative x1 plus 3x3. So if you take the transpose of this guy, you get exactly what we have in here. Okay? In that case, if they give you a matrix, you can find the formula of linear transformation. Okay? Look at this. If they give you a matrix A, S1, negative 2 and 5, 2, 0 and 3, 4, 0 and negative 2. They ask you to find the T. Let's say TA, right? The linear transformation corresponding to this matrix. So you just apply this matrix to some vector x. You have 1, negative 2 and 5, 2, 0 and 3, 4, 0 and negative 2. Apply to x1, x2 and x3 or x, y, z, whatever you want. You have x1 minus 2x2 plus 5x3, 2x1, 0x2 plus 3x3, and then 4x1, 0x2 again minus 2x3. And you write tx or t x1, x2, x3 is the transpose of this guy, okay? So you have x1 minus 2x2 plus 5x3, 2x1 plus 3x3, and 4x1 minus 2x3. So that's how we can write the formula of linear transformation if we know X matrix. Here I want to mention one thing. If you apply this linear transformation to basic vectors in the standard basics of R3, what will we get? You apply A to 1, 0, 0. You get 1, negative 2, 5, 2, 0, 3, 4, 0, negative 2, 2, 0, 1, 0, 0. So basically you just plug 1, 0, 0 into this formula, right? And you get the vector 1, 2, and 4. What's that? That is the first column of A. You see that? That is the first column of A. Similarly, if you consider A 1, 0, 1, 0 in here, you will get the second column of A, which is negative 2, 0, and 0. And then A 0, 0, 1, that is the third column of A. So basically, this matrix, the matrix A, sometimes is called the representation of linear transformation in the standard basics. Okay, I write here. That is representation of T in the standard basics. What does it mean? That means if you change the basics, you would have another representation. Makes sense? You know, I mentioned several times when we study matrices, we say matrices are elements of some vector space, right? And what we see in here, that is just representation of the matrix in some basics. And we also study, you know, transition matrix, how to go from one to another basics. And we also know how to change the coordinates, right? So, you know, in this situation, if you work with linear transformation and you work with different basics, you also may apply the same technique to go from one to another basics. And you can find the representation matrix of some linear transformation with respect to the new basics. All right? If we don't say anything about the basics, we suppose that we are working with the standard basics. Okay? So let's consider the following example. We need to find the standard matrix for the following linear transformation from R3 to R2 such that T, X, Y, Z equal to X minus 2Y and 2X plus Y. Look at this. We might do wrong in this example. So our transformation goes from R3 to R2. As we learned in the previous video, the corresponding matrix T, AT of the T, will be the matrix of the size 2 by 3, right? But, you know, like previous example, if we want to write the matrix of this linear transformation, I just need to pick coefficients, right? And for this example, if I pick coefficients of these linear transformations, I get AT would be equal to 1, negative 2, 2, and 1. This is just 2 by 2 matrix. So there's something wrong in here, right? There's something wrong in here. All right, so how to find the standard basics, a standard matrix for this linear transformation? I will use the remark we just did right here. So I will pick vectors in the standard basics for R3. And I apply T to those vectors to get columns of the matrix for this linear transformation. Make sense? So my T 100 is what? That is 1 and 2. So this is the first column of AT. I apply 0, 1, 0. I will get negative 2, 1. This is the second column of AT. And I still have one more, T 0, 0, 1, which is just 0, 0, because we don't have Z in the formula of T, right? X and Y are 0. So this is the third column of AT. From this, I will get AT equal to 1, 2, negative 2, 1, and 0, 0. So we have 2 by 3 matrix. And actually in this situation, AT is the representation of T with respect to the standard basics, or we say that is the standard matrix of this linear transformation. Okay? Suppose now you have two linear transformations. You want to consider a sequence of these two linear transformations. How to find that? Like you are here, okay, you go to next one via T1, I say X, here is Tx, and you go from Tx1 to Y, which is equal to T2 T1x. So you just realize a composition of these two linear transformations. Make sense? And how to find this guy. Okay, so we just saw that for T1 you have A1. Okay, for T2 you also have A2. The question is, can we use A1, A2 to create the composition of these two linear transformations? The answer is yes. And how? When we study matrix multiplication, we say the multiplication A with the B is just consequence. Remember that when we study matrix multiplication, A times B, we say if you want to apply this product to some vector x, right? So you have to apply B to the x first. That is just A, Bx. Make sense? So if you compare this form and this form, you would think, all right, so for T1x, I would have B right here, right? Make sense? And for T2 right here, that is corresponding to 2A. So if you want to use matrix product to realize the composition of two linear transformations, so you would do the following product. We write product A, right? But which one is the first? You would have T1 in here, so that is A1, and you have A2 right here. Make sense? So that is associated to this formula. When you have an X, right? When you have an X in here, which is right here, so you will apply A2 to A1X. That is T1. Make sense? So overall, from this picture, you define the following one. If you have T1 and T2 are two linear transformation, let's say T1 from V1 to V2 and T2 from V2 to V3, where V1, V2, V3 are vector spaces. So you might consider a composition of T2 with the T1, which is equal to T2, T1, okay? And here I say just dot, means in case if you have vector, you just write vector right there. And the AT is equal to A2 times A1. All right? So let's consider the following example. You have T1, X, Y, and Z equal to 2X plus Y, 0, X plus Z, and T2, X, Y, Z equal to X minus Y, Z, and Y. Both of them are linear transformations in R3. Okay, in R3. And we have matrix A, T1, that is 2, 0, no, 2, 1, 0, 0, 0, 0, and 1, 0, and 1. From the formula of T2, I have TA2 equal to 1, negative 1, 0, 0, 0, 1, and 0, 1, 0. Now I want to find superposition of T1 and T2. I have T2, T1 equal to, I can write A of this, make sense? Just equal to A T2 times A T1. Okay, so we just need to find product of 1, negative 1, 0, 0, 0, 1, 0, 1, 0 times 2, 1, 0, 0, 0, 0, 1, 0, 1. And let's multiply them. The first row with the first column is 2. The first row with the second column is 1. The first row with the last column is 0. The second row with the first column is 1. The first row with the second is 0. This is 1. And then we get 0, 0, and 0 in here. Okay? So that's what you get, composition of T1 and T2. All right, now if I want to find composition of T1 and T2, like T1 dot T2, okay, I need to find A. So if I interchange this, I would interchange the AT1 and T2 in here. So I have AT1 times AT2. Make sense? And I have 2, 1, 0, 0, 0, 0, 1, 0, 1 times 1, negative 1, 0, 0, 0, 1, 0, 1, 0. And when you multiply them, you get first row with the first column is 2. First row with the second is negative 2. The first row with the last is 1. The second row is just 0, 0, 0. The last one is 1 right here. And then 0 and 0. So you see, they are different, right? Of course, because matrix multiplication is not commutative. All right? So, you know, composition of two linear transformations can be realized using matrix multiplication. When we study matrices, we talk about the inverse of a matrix, right? The inverse of a matrix. And we know how to find the inverse if it exists. Okay, so using composition of linear transformations, we may talk about the inverse of linear transformation. All right, so see, you have some x in here in the first space A, let's say V1. You have another space V2. You go from x to y via t. So if you consider another linear transformation from V2 to V1, right? And if that guy will send this y back to the x for any x and y, so t to negative 1 is said to be the inverse of t. Make sense? You know, this situation is very similar to functions. There's nothing special. Agree? So how to find the inverse in this situation? Yes, you have t, so you have at right here. If you have t to negative 1, you also have at to negative 1. And when you apply at and at to negative 1, you get the identity. So that means if you apply t with the t to negative 1, x, it should be y, right? And that is equal to y. If you apply t to negative 1 with the t, x, you will get x. Okay? So that is the two identities if the t is invertible. And when you apply the second equation with the matrices, so you would get the following one. You would get a t to negative 1 times a t equal to 1. Means identity matrix. Because, you know, this sends x to the x, right? You see that? So that means, you know, this matrix should be identity. But what does it mean? That means at to negative 1 is just at inverse. In this case, we talk about square matrices, right? Or we are talking about linear transformations in the same space. So we have this identity. That means in order to determine the inverse of a linear transformation, if as x, we just apply the inverse of the matrix of that linear transformation. Right? Let's consider the following example. We have t from R3 to R3, such as t x1, x2, x3 equal to 2x1 plus 3x2 plus x3, 3x1 plus 3x2 plus x3, and 2x1 plus 4x2 plus x3. We don't have any problem with such linear transformations when we need to write the matrix, because we are in the same space R3. So I just need to pick all coefficients. 2, 3, 1 in the first row, 3, 3, 1 in the second row, and 2, 4, 1 in the third row. I need to test if this matrix is invertible or not. If this matrix is invertible, then our linear transformation is invertible. Make sense? Invertible or not? For that, we just need to test the determinant, right? At, you can find determinant easily. Let me write that in here. I have 6. I will use diagonal. Plus 6 plus 12 minus 6 minus 36 and minus 9. I don't need a concrete, an exact number, but I know this is not 0. So the matrix At is invertible. You know how to find the inverse of this matrix. So I will not repeat that. I just write in short, negative 1, 1, 0, negative 1, 0, and 1, 6, negative 2, and negative 3. This is the inverse. And as we discussed previously, that is nothing but a of t to negative 1. right? So you can write the inverse of this linear transformation. T to negative 1, x1, x2, x3 is nothing but negative x1 plus x2. So I just pick, coordinates of the first row, right? And here is negative x1 plus x3 and 6x1 minus 2x2 minus 3x3. That's how we can find the inverse of a linear transformation if it exists. Now let's talk about how to find matrix relative to a non-standard basics when you go from one basics to another, right? We have linear transformation T in R2 such that Txy equal to x plus y, 2x minus y. They ask us to find the matrix for T relative to the basics B. It's obvious that B is a basics for R2. Why? Because the matrix 1, 2, negative 1, 1 is invertible. This matrix has non-zero determinant, right? So B is a basics for R2. Now how to find the matrix for T with respect to these basics? In the above example, when we study the matrix A for T, we mentioned one thing. If you have T like this, so the matrix A is 1, 1 and 1, negative 1. What is the first column? The first column is nothing but the 84, 1, 0, right? The second column is 80, 0, 1. Makes sense? So basically, if you write this in the form of matrix product, you would have the following one. That is just 80 equal to 1, 2, 1, negative 1, multiply with 1, 0, and 0, 1. Make sense? Because, in the result, you would get the representation of T with respect to these basics. And now, if you want to find the matrix for T with respect to another basics, you almost do the same thing. Make sense? But instead of this column and instead of this column, you have vectors from the new basics. Agree? So I would write like this. This is the representation, the matrix of the T with respect to the standard. Now I want to find the matrix of T with respect to new basics, or in this case we have B, that is nothing but 1, 1, 2, negative 1, which is equal to the standard representation of T, right? Multiply with 1, 2, no, multiply with 1, 2, yes, 1, 2 right here, okay? That is the first vector in B, and negative 1 and 1. So that gives you 3, 0, 0, and negative 3. Make sense? And this is the matrix for T in the basics B. Agree? So from here, probably you can guess. If you have another basics B prime, you can solve, you can find the matrix for T with respect to B prime. How about that? If you have solution, please send it to me. Right? Thank you for watching. And in the next video, we will study different spaces associated to a linear transformation. Bye.